Now that we have an understanding of atomic structure and the behavior of valence electrons, let's look at the type of chemical bonds that can form. So chemical bonds are produced through chemical reactions. So chemical reactions are the making or breaking of chemical bonds, leading to a change in the composition of matter. So we have two molecules of hydrogen here, one oxygen molecule. They each have their own individual properties. But when you change the bonds in these molecules and produce something new, they have different properties based on that new composition. So if we combine two hydrogen molecules with an oxygen molecule, we end up with H2O, or water. So in this reaction, we have changed the composition or the makeup of these bonds and produced an entirely different piece of matter. Just sort of general characteristics here. On the left side, we have the reactants. The arrow indicates that a reaction is taking place, and on the right side, we have the products. So you can sort of think of this as the starting molecules and the end result. The rate at which a reaction will take place depends on several different things. Now, first of all, reactions are reversible. Just depends on the conditions. So most chemical reactions will take place in a forward and reverse direction at the same time, which means your reactants are being converted into products. And at the same time, your products may be breaking down back into the reactants. Now, chemical reactions often require heat. That's where they get their energy to go. So depending on how much energy or heat you need to put into this reaction will depend on which direction it's going to go. The concentration of the reactants and the concentration of the products is going to affect the reaction rate. So if you have a really high concentration of products, so high concentration here, that's going to mean that hydrogen is going to encounter nitrogen much more frequently. And when they encounter each other and there's enough energy present, they're going to form NH3. And NH3 is ammonia. As the concentration of NH3 or ammonia increases, there's going to be less hydrogen and nitrogen to encounter one another. So it's going to be less likely that you're going to produce more ammonia. And that causes the reaction to slow down a little bit. Eventually, a reaction is going to reach chemical equilibrium. Chemical equilibrium means that there's no change in the concentration of reactants and products. This does not mean that the reaction stops. What it means is that the conversion of reactants into the product is happening at the same rate as the dissociation of the products back into the reaction. So we say that the forward reaction rate and the reverse reaction rate are the same. So there's no net change in what we have available. There are 4 types of chemical bonds that you need to know. And we are going to go through each of those. There are 3 major categories, covalent, ionic, and hydrogen bonds. And then within covalent, there are 2 different types of covalent bonds, nonpolar and polar covalent. So we're going to talk about the chemical properties of each of these and why the bonds are different you will need to be able to identify or describe how these bonds occur and why they might be biologically important. So covalent bonds form when two atoms share electrons. Now, I have sort of a silly way to remember what these mean. I like to think of covalent bonds as sort of like a marriage. So they're sort of in the realm of bonds, they're sort of permanent bonds, if you will. So that's why I like to think of it as a marriage. It's a long-term agreement, if you will, in which the elements share electrons between them. So if you think about a marriage or even just a long-term relationship, you share a lot of things, right? So in a covalent bond, you have two atoms sharing their electrons. Now, in the last video, I talked about valence. Remember, valence is the outermost shell. The valence shell is the outermost shell in an atom. And in that valence shell, you have unpaired electrons. And those electrons like to be in pairs. They like to be in a relationship. So here we have hydrogen. Hydrogen only has one shell, so its shell is the valence shell, and hydrogen has one electron. Now that electron wants to be paired with somebody. It wants a significant other, and it often finds its significant other in other hydrogen molecules. So what happens here is the negative charge from those electron clouds around the nucleus is attracted to the positive charge of the protons within the atomic nucleus. So this electron is attracted over here, this electron is attracted over there, and they sort of start to spend more time together. You can kind of see how this is kind of parallel to a relationship. So they start sharing things. They start sharing their electrons. Now, that does not mean that this proton actually takes an electron away. This is a mutually beneficial relationship. They're sharing it. So what happens is the electrons just start spending more time together in between these nuclei. So a covalent bond forms when those electrons bring the protons together, bring the atoms together. And what you get is sort of this filling of both of the shells, because while they're sharing their electrons, both of the valence shells are filled, which makes those two hydrogen atoms happy, and it makes them stable. So covalent bonds work because of something called electronegativity. Electronegativity is the attraction of a particular atom for an electron. So if we're thinking about a long-term relationship, really strong friendship, or a marriage, they work when both of you like each other, right? When both of you are attracted for some reason. So you can think of electronegativity as an attraction, a level of attraction. So some atoms share their electrons to varying degrees. So some atoms are really electronegative. That means they strongly pull atoms to their core. So strongly electronegative, atoms pull electrons toward their nucleus. Now, some are not as strong. Their electronegativity is lower, and they don't pull them quite as strongly. I had that picture of the periodic table, and one of the things I mentioned was electronegativity tends to increase going right to left. Sorry, left to right. Left to right. Now, you might remember that hydrogen was on the left, and over here on the right, we had carbon, nitrogen, and oxygen. Hydrogen has very low electronegativity. It has problems keeping its electrons to itself. Nitrogen and oxygen, though, have really strong electronegativity, and they like to pull electrons towards them, which is why they tend to bond very frequently with hydrogen. So electronegativity is going to affect our other types of, our two types of covalent bonds. So nonpolar covalent bonds are bonds where atoms share valence electrons equally. So I like to think of this as like a perfect relationship where everything's good, everything is shared, everything is equal amongst the two individuals. So there's equal attraction for those electrons because there's equal electronegativity. One's not like more needy than the other. One's not pulling that electron more strongly. Now, nonpolar bonds tend to mostly form between two identical atoms, because if there's equal sharing, you need equal pull, and you get equal pull when you have the same type. So oxygen will actually form a double bond with itself, and each oxygen molecule has 5 valence electrons. So it has 2 in the outer shell that it can share. So it actually likes to share 4 between it, and you get this nonpolar covalent molecule. Now, the other biologically important nonpolar covalent relationship is carbon and hydrogen. Carbon and hydrogen are on different sides of that periodic table, but their electronegativities are very, very similar. So carbon and hydrogen are pulling electrons with the same electronegativity, the same amount of attraction towards its nucleus. So carbon and hydrogen, often found together, are biological molecules are almost exclusively formed by carbon and hydrogen. And carbon likes to make nonpolar covalent bonds with itself, and it likes to make nonpolar covalent bonds with hydrogen. And so you can end up with these really big, complex carbon and hydrogen molecules, which are the basis of most of our biological molecules. Now you're probably thinking, oh, these electrons are shared equally. What happens when they're not? Well, when they're not shared equally, I like to kind of think about this as like a bad relationship, where one person is always giving and one person is always taking. In polar covalent bonds, we see that relationship where electrons are not shared equally. So this happens when an atom is bonded to a more electronegative atom. And what happens is that electronegativity distribution creates an unequal charge for the molecule as a whole. So a few minutes ago, I said that oxygen and nitrogen were very electronegative. So oxygen is highly electronegative, and hydrogen is not. Oxygen and hydrogen form water. When this happens, oxygen pulls those electrons from hydrogen towards its core. So those electrons spend more time being pulled towards the oxygen. When that happens, you get a charge accumulation, a negative charge accumulation, because those electrons are negatively charged towards the oxygen. And what happens is something called polarity. Now, you might be familiar with polarity. Polarity means that something has a direction. So in this molecule, the negative charge from those electrons accumulates around the oxygen, and the positive charge accumulates around the hydrogen. And that's what this little symbol here is showing. It's showing you that there's a negative charge towards the oxygen and a positive charge on the hydrogen ends. And that makes this what we call a polar molecule. So we will come back to polar molecules in just a few minutes, but let's move on to other types of chemical bonds. The second type of bond, third one that we're going to talk about, is ionic compounds. So I like to think of ionic compounds as a really bad relationship. So in ionic compounds, two atoms' electronegativity are so unequal that one atom completely strips an electron from the other. And the result is something called an ion. An ion is simply a charged atom. Now, this is different from polarity, because in polarity, you get regions of a compound or regions of a molecule that are charged. But this is an entire atom that has gained a charge. So if we look at this example of sodium and chlorine atoms, you'll see that sodium has 1 valence electron and chlorine has 7. So in order to fill sodium's valence shell, it would need 8 more electrons. Well, something forming 7 more electrons. Something forming 7 bonds, if you will, for those electrons is not going to happen. But filling chlorine's shell with 1 electron can happen. Basically, 1 bond is forming. So what happens is that chlorine actually attracts that electron so strongly that it pulls it out of sodium's valence shell and completes chlorine's valence shell. So when that happens, sodium has lost negative charge, which means it has become more positive. Chlorine has gained negative charge, which means it has become more negative. These charged molecules are called ions. A positively charged molecule is called a cation, and a negatively charged molecule is called an anion. So those are just terms that you're going to need to remember. Now, ionic bonds are important because they can lead to ionic compounds. An ionic bond is a little bit of a misnomer because ionic bonds are actually attractions, not atoms being physically bound. So when we saw our covalent interactions, they're actually sort of stuck together. Those 2 hydrogens, or the oxygen and 2 hydrogens, are stuck to one another. They're not going to come apart very easily. But in ionic compounds, they're actually attracted to one another. So that positively charged sodium is attracted to the negatively charged chlorine. They're not stuck together. They're just sort of hanging out. So I guess maybe marriage is not a good analogy for this one, but they're still attracted to one another. That positive charge on the sodium is attracted to the negative charge on the chlorine, and that keeps them together. Ionic compounds will arrange themselves in a really nice 3D structure. So if you look at the molecular structure, you have this alternating between chlorine and sodium because those sodiums are positively charged and those chlorines are negatively charged, and they are being attracted to one another. Now, because they are attractions, they're easy to break apart. Ionic compounds are very often soluble in water. I'd like you to pause for a minute and think about why they might be soluble in water. Think about water's polarity and sodium and chlorine's charges. So I don't know if you paused it or not, but I'm going to tell you why if you didn't. So remember, our water molecule is an oxygen and 2 hydrogens with that partial negative and partial charged regions. Ionic compounds are soluble in water because those positive hydrogen regions are going to interact with the chlorine, and the negative oxygen regions are going to interact with the positively charged sodium and sort of break apart this ionic compound, because that water molecule's charge is going to interfere with the attraction between the sodium and the chlorine, which is why you can dissolve salt in water. Our last classification are weak chemical bonds. Now, there are different types of weak chemical bonds, but we are going to focus on hydrogen bonds, because water and other polar bonds, hydrogen bonds, are central to the chemistry of life. So when we looked at the water molecule, we said that water produces these electronegative regions. Now, when you look at a water molecule, you will see that you've got that positive and the negative region. And just a minute ago, when I was showing you ionic compounds, I told you that those regions can interact with other molecules. Well, they can also interact with other polar molecules. So example here on the left is water interacting with ammonia. So oxygen is highly electronegative, which means it pulls electrons towards itself. So is nitrogen. And so we get this same unequal charge distribution in ammonia. And so the positive hydrogen region of the water can interact, not form a bond with, but sort of form an attraction with the negative region of that ammonia. And we form something called a hydrogen bond. Now, that hydrogen bond is really just an attraction between the positive region of hydrogen in these molecules and the negatively charged region in another molecule. So hydrogen bonds are attractions between polar molecules. And the most important polar molecule is water. Now, water forms hydrogen bonds with itself. So you have the negatively charged oxygen attracted to the positively charged hydrogen, and you get this sort of very regular structure where your positive and negative charges sort of make the water molecules spread out. And that spreading out, those hydrogen bonds and this regular structure of water molecules give us some very important properties that allow water to be probably the most important element for life. So that hydrogen bonding gives water some really special properties and characteristics. So we'll talk about those properties of water in just a little bit. Characteristics are that water molecule is sort of V-shaped, with your oxygen at the point and your hydrogens forming the sides. And then, of course, it is also polar, with this largely positive region over here and largely negative region over there that allows for those polar hydrogen interactions.